So we are building a building with Jackson Simmons and Ben Summers. We're going to show you what we did. We put together a 12-story school, and in this 12-story school, we have put it together so it's easier for kids to get higher education, just because it's a taller school. Also because the live load and dead loads are fairly consistent, with not a huge amount of moving compared to an office building or some kind of pool or other hallway where you get tons of movement of offices and desks and everything. Our building is 15 stories tall, with the first 14 being 3 meters and the bottom one being 5 meters tall. The building is a 25 by 25, and the floors are 125 millimeters thick, and the top roof is 100 millimeters thick of concrete. We have used for all of our columns, we used HSS's, which was 32 by 32 by 5/8 of an inch, and we used an I-beam by S, that is S12 by 31.8. The building layout that we have chosen is a 3 by 4 by 3 with 2 rows of 3s on the outside and then a row of 4 right down the middle, and right across the 2 middle columns in the middle there's a beam that is unsupported there, that is 11 meters long. The tributary areas for them breaks down like this, where this is for the columns and this is for the beams, with these two being the largest tributary areas and then these two being the largest with combined loading. Well, the beam only having one to compete, so that is the maximum loading on it. The total loads that we've put together are for the dead loads, we have a concrete load of 1.6 kPa, which is using the mass of the concrete times the thickness that we have for the roof. And then for the roof we have the live load, which is 1 kPa from the standard, and then we have the snow load, which is 2.8 given in class. We use the case load number 3 to find the factor load on it, which is 5.63 kPa. Then for the loading on the floors, we used case 2 and the dead load from the concrete, and then the live load, which was given in the Ontario Building Code standard, which was 2.4 for schools. And using case 2 again, we found it 6.11 kPa. The moment of the inertia on the I-beam, we solved it by solving for the entire square of the I-beam, and then solving for the middle 2 rectangles, and then subtracting the middle 2 out, and only having the I-beam left. The bending stress on the I-beam, we got the forces acting on it, which is the force going down on it times the width, and then multiply the maximum moment, which we got from the NDS design sheets for a UDL on a held column, or beam, sorry. And then the bending stress we found using the My/I equation to find that the bending stress is 242 MPa on the roof. And then on the flooring we did the same thing, finding the bending stress is 263 MPa. And then we found the max deflection on the beam, and that is, for the roof we used the equation 5WL to the 4th divided by 384 EI. Using that equation we found that the max deflection on the roof was 36 millimeters, and then on the floor it is 39 millimeters, when the allowable deflection using L over 240 is actually only 39.6, so we are just barely under. I'm giving this off to Ben. He's going to do the columns.
So the moment of inertia found in the columns is by using the finding the moment of inertia for a completely solid column, then minusing the moment of inertia within the hollow portion of that column, as represented by the calculations here. Let me just, there we go. So the total loading on the middle north column is represented by the roof forces times by its area given here, and the floor forces times by its tributary area, and then all of that quantified to with all 14 floors and the roof is shown here. So max shear and point critical of the columns are represented by finding the area of the material within the column, similar to the finding the moment of inertia of the column, finding the whole area, minusing the hollow area, giving you the area of the material itself. And using the force found previously on the bottom column divided by that area gives us our max shear stress, which is 345 newtons per millimeter squared. After that, what we found was the point critical of the piece of column on the bottom floor, where it is 5 meters tall, or 5,000 millimeters, represented by Euler's equation here. And for the eastern column, very similar to finding the forces acting on the middle column, was quantifying the force acting on the roof, force acting on the floor, and then adding them up together, represented by the numbers here. Next was to find the wind loads acting on that eastern column, because it is the column directly next to the wall. So we have our force given, our wind load here. Then using case number 2, we found that the true force was 1.28 kilonewtons per meters squared. Then using the width of the wall, we found that the force acting on the column was 16 kilonewtons per millimeter. After that, we found the max moment by using the NDS pamphlet thing, whatever you call it. And afterwards, we found the combined stresses by putting all the loads in, area, and the my over I equation to find our combined stresses, which is shown here at the bottom. So our maximum loadings are all in check for the building itself, represented by the maximum loading that the column can support being here, and our column's force that is acting upon it here, our maximum yields of steel being just over the actual bending stress on the final column, and also our maximum yield for steel again with our beam and our maximum bending stress on that beam itself with all the loadings on top of them, with as well the allowable deflection and our max deflection on the floor. Another check for the loading is the extra 75% increase. So with an extra 75% increase on the bottom column, it is still underneath the point critical of that column, as well as the though the column's point critical is much larger than the plus 75% increase in loading, the MPa, when it's added another 75%, fails. So that is where our building fails when it comes to an extra 75% increase. A way to fix this is to add another layer of steel completely around the columns, be it a meter thick column or just another layer over top of it all. And that is our presentation.